Hi students, Professor Nugent here. In this video, we are going to talk about control variables and conditional mean independence. To think about control variables, we are going to rely on our example of test scores. We want to get an unbiased estimate of the effect on test scores of changing class size, holding constant factors outside of the committee's control. Factors that are outside the committee's control include things like learning opportunities, such as museums, parental involvement in education, such as reading with mom at home. The reason is that the committee is interested in what the committee can change in order to improve test scores. So we want to focus on those factors, holding constant the factors that the committee cannot change. If we could run an experiment, we would randomly assign students and teachers to different sized classes. Then the student-to-teacher ratio would be independent of all other factors that go into the OLS residual, so that the expected value of the OLS residual given the student-to-teacher ratio would be 0. And the OLS slope estimator in the regression of test score on the student-to-teacher ratio would be an unbiased estimator of the desired causal effect. Recall that we have defined the causal effect as the effect that we would estimate in an ideal randomized controlled experiment. However, we are not often in the scenario in which we can run a randomized controlled experiment. We're working with observational data. And with observational data, the OLS residual U depends on additional factors, such as parental involvement, knowledge of English, access in the community to learning environments outside school, etc. If you can observe those factors, such as percent of students learning English, then you can include them in the regression explicitly. But usually, you cannot observe all of these omitted causal factors, such as parental involvement in homework. In this case, where we cannot directly, explicitly observe the omitted causal factors, but we want to include them, we can include control variables that are correlated with the omitted causal factors, but which themselves are not causal. In other words, we can include some kind of proxy serving as a control variable. Students, I know how to spell control. Okay, very good. Control variable. Great. So we can look for a proxy for these omitted causal factors. But if we use a proxy, they may not have a causal interpretation. Formally, a control variable W is a regressor included to hold constant factors that, if neglected, could lead the estimated causal effect of interest to suffer from omitted variable bias. So if we left out something like parental involvement, then our estimate of the effect of student-to-teacher ratio on test score may suffer from omitted variable bias. We can try to use proxies, control variables, to get at these omitted factors. Here is an example. We're still with our test score regression, where we are regressing test score on the student-to-teacher ratio. We have included the variable PCTEL, which represents the percent of English learners in the school district. And we have included another variable, which is LCHPCT, the percent of students receiving a free or subsidized lunch. Only students from low-income families are eligible, and so you are getting the percent of students, a proxy for the percent of students who are low income. So let's think about which variable is the variable of interest here, which variables are control variables, might they have causal effects themselves, what do they control for? Well, we know that the student-to-teacher ratio is the variable of interest. That is the variable that the committee can control. Percent of students learning English may have a direct causal effect because school is tougher if you're learning English. Taking tests in a language that is not your native language is more difficult. But it is also a control variable, as immigrant communities tend to be less affluent and often have fewer outside learning opportunities. Therefore, this variable, percent of students learning English, is correlated with those omitted causal variables. So this variable is a possible causal variable and a possible control. It's definitely a control variable. Now, lunch percent might have a causal effect because lunch helps learning, eating lunch helps learning, but it is also correlated with and controls for income-related outside learning opportunities, which are very important. So if we cannot explicitly measure and include income-related outside learning opportunities, we can include a proxy for those opportunities, include lunch percent as a control variable. It may have a causal interpretation. We will come back to that shortly. I want you to think about it. So, including control variables, there are 3 interchangeable statements about what makes for an effective control variable. 1. An effective control variable is one which, when included in the regression, the control variable makes the error term uncorrelated with the variable of interest. Now that's huge, right? Because once the error term is uncorrelated with the variable of interest, then the OLS estimate of the coefficient on the variable of interest is unbiased, does not suffer from omitted variable bias. 2. Holding constant the control variables, the variable of interest is as if randomly assigned. And we get the same thing from this result, that the OLS estimate of the variable of interest is unbiased. Holding constant the control variables. 3. Among individuals or entities with the same value of the control variables, the variable of interest is uncorrelated with the omitted determinants of y. We're saying the same thing here. The variable of interest will be uncorrelated with the OLS residual among individuals or entities with the same value of the control variable, or holding constant the control variables. So it's very powerful to include control variables because that makes our OLS estimate of the coefficient on our variable of interest unbiased. It helps us take care of the omitted variable bias problem. Now, control variables need not be causal, and their coefficients generally do not have a causal interpretation. Let's look at this test score example where the coefficient on lunch percent is negative 0.547. Does the coefficient on lunch percent have a causal interpretation? Well, if it did, then we should be able to boost scores by a lot by simply eliminating the school lunch program, setting lunch percent equal to 0. Eliminating the school lunch program. Okay, so let's think about this. Eliminating the school lunch program has a well-defined causal effect. We could construct a randomized experiment to measure the causal effect of this intervention. We would expect that eliminating the lunch school program would decrease test scores, right? Because students need access to lunch, period. So you would expect that there would be a positive coefficient if we were making a causal interpretation on this variable. But we're not. This variable is only serving as a control variable. So this control variable, lunch percent, has a negative coefficient, right? Which means that the more students that are in lunch percent, the less the test score. So this is just serving as a control variable, as a proxy for the other things that are highly correlated with lunch percent. This is not a causal interpretation which says that the more students you give access to lunch, the less test scores you get. That's not a causal interpretation. This is not something that we got out of a randomized experiment. Not at all. This is just a proxy for the other things, the income-related access to educational opportunities that are correlated with lunch percent. That's what's being captured here. And that's why we have a negative sign in front of lunch percent, because the more students that you have in that program, the more students that are in the district that don't have as much access to income-related education opportunities, and that's why there's a negative coefficient. So it's not a causal interpretation on this variable. It's just a control variable so that we can have a causal interpretation on our student-to-teacher ratio. Right? Our lunch percent is capturing those income-related factors, so that student-to-teacher ratio is no longer correlated with those income factors in the residual.